Let omega 1 and omega 2 be circles intersecting at A and B. Point C lies on omega 1 and D lies on omega 2 such that AD and BC are parallel. Lines AC and BD intersect at S. Assume that S lies outside both omega 1 and omega 2. Prove that there exists a point U on omega 1 and a point V on omega 2 such that line SU is tangent to omega 1, line SV is tangent to omega 2, and line AB bisects UV. So we have two circles here, omega 1 and omega 2. They intersect at points A and B. And point C is chosen on omega 1, with point D chosen on omega 2, such that AD and BC are parallel. And we're going to let lines AC and BD intersect at point S. We need to prove that there's a point U on omega 1 and a point V on omega 2, such that line SU is tangent to omega 1, and line SV is tangent to omega 2, and line AB bisects UV. So for point U, there can only be 2 points U such that line SU is tangent to omega 1. Let's draw both tangents from S to omega 1. Those are the two possible locations of point U. This is U. Let's call them U and U prime. And similarly, for S and omega 2, there's exactly 2 points V on omega 2 where SV is tangent to omega 2. Let's draw both of those in. It's going to look something like this. We'll call this point V prime, and this point here is point V. And we need to prove that either UV prime, UV, U prime V, or U prime V prime, one of those 4 segments is bisected by line AB. So it doesn't look like segments UV prime or U prime V are bisected by AB. We can ignore those, and instead we can just focus on one of UV or U prime V prime. I'm going to pick UV to focus on, and we need to prove that it is bisected by line AB. So let's look at the entire diagram. And do we see anything interesting here? Well, it certainly looks like the angle formed by USU prime is equal to the angle formed by VSV prime. In other words, it looks like SU prime and SV prime are isogonal with respect to angle USV. So we conjecture that that statement is actually true, that SV prime and SU prime are isogonal. But we need to prove our conjecture first. Let's see how we can do that. And I think the best way to do that is to focus on point S. Let's go back to what point S is defined as. It is defined as the intersection of lines AC and BD, where C is a point on omega 1 and D is a point on omega 2, such that AD and BC are parallel. So this suggests we need to use the parallel lines somehow. And indeed, we see that the power of S with respect to omega 1 and the power with respect to omega 2, if we find those powers, we might be able to use the similar triangles somewhere. So let's do something related to that. We know that SC times SA over SB times SD is equal to SU squared over SV squared. Because the numerator is the power of S with respect to omega 1, and the denominator is its power with respect to omega 2. So SC times SA over SB times SD. And here's where we can use the similar triangles. We know that SC over SB, because of the parallel lines, that's equal to SA over SD. So we can also say that this is equal to SA over SD squared. But in addition to that, SA over SD is equal to SC over SB. It's also equal to SC over SB squared. So SA over SD is equal to SC over SB. And remember that if A over B equals C over D, then that common quantity is also equal to A minus C over B minus D. So this is equal to AC over BD squared. Now that's something interesting. We can use the parallel lines again for AC over BD. Because the parallel lines create equal angles here and here. And AC over BD, well, what's AC? Well, that's just 2 times the radius of omega 1 times the sine of angle ABC by the extended law of sines. So it's 2R1 sine angle ABC. And BD is equal to 2 times the radius of omega 2 times the sine of angle BAD. But these are the same angle because the lines are parallel. They're alternate interior angles. We can cancel the 2, cancel the equal angles, and this is just R1 over R2 squared. So SU over SV is equal to R1 over R2. And now we can create similar triangles by connecting U and V to the centers of the respective circles. If we connect U to center O1 and V to O2, formed by the perpendicular to SU at U and the perpendicular to SV at V, then triangle SUO1 is similar to triangle SVO2 because they're both right triangles for one. And the other thing is that SU over SV equals R1 over R2, which is UO1 over VO2. Now consider what happens if you duplicate these triangles by reflecting them over their hypotenuses. They will get mapped to 2 kites known as SUO1U prime and SVO2V prime. So these kites are spirally similar to each other, we can conclude. And therefore, by the spiral similarity of the kites, we have that angle USU prime equals VSV prime, which is our original conjecture. We have proven that SU prime and SV prime are isogonal with respect to angle USV. Now, if you look for a moment, what else is true about this configuration? Well, we have that S is the unique spiral center that sends segment UU prime to segment VV prime. And that spiral center is none other than the Mikel point of quadrilateral UU prime VV prime. And another useful property of the Mikel point is that it is also none other than the intersection of the circumcircles of triangles XUU prime and XVV prime. If X is this point where UV prime and U prime V intersect. So if X is that point, then X on both the circle formed by the Mikel point U and U prime and the circle formed by SV and V prime. XSU prime U and XSV V prime are both cyclic. So let's draw in those 2 circles. And it's worth noting that those circles will both pass through the centers O1 or O2 because of the kite condition from earlier. Angle SUO1 equals angle SU prime O1 equals 90. So SO1 is the diameter of the circle. A similar condition applies to SO2. There we go. So we have the 2 circles. Now, you might notice something else that looks a little interesting. It looks like XO1 and O2 are collinear. And this is actually not that hard. You'll see why it's the case if you just look at the diagram for a little longer, because SO1 and SO2 are diameters basically, and X lies on both of them. So angle SXO1 equals angle SXO2 equals 90. So not only are XO1 and O2 collinear, X is the foot of the altitude from S to line O1, O2. And if you look at the diagram for a few more seconds, you might notice something else. Now, given that XO1 and O2 are collinear, looking at point O2, we notice that V prime and V both lie on the circle with diameter SO2, and they're both equidistant from point O2 because they're both radii of omega 2. So O2 V prime equals O2 V. And that implies by fact 5 that line XO1O2 is indeed the angle bisector of the two lines formed by XU V prime and XU prime V. So if line O1, O2 is the angle bisector of those two lines, and they both pass through X, we notice how each of the lines XU V prime and XU prime V intersect the two circles, omega 1 and omega 2, in 4 different points. As you can see here, if you were to just extend line XU V prime a little bit, for example, you'll see that it intersects the two circles in 4 different points. So if you just did a reflection over O1, O2, it should still intersect the two circles in 4 different points. And the 4 new points, furthermore, must all be the reflections of the original 4 points over O1, O2. So I'm going to label the original 4 points formed by XU V prime intersect the two circles. I'm going to let XU intersect the first circle at U and U1, then the second circle at V prime and V1 prime. There we go. And then its reflection over O1, O2, which is XU prime V, it's going to intersect the first circle at U1 prime and U prime. And then the second circle at V1 and then V. So what do we notice about this configuration over here? Well, if you saw earlier, let's get back to point S for a little while. We know that it's the spiral center that sends U prime to V prime V. But what else? Well, if it's the spiral center that sends U prime to V prime V, it's the Mikel point of that quadrilateral. But that means it would also send U V prime to U prime V. But SU equals SU prime because they're tangents. And SV prime also equals SV. They're tangents to the same circle. So this spiral similarity is nothing but a rotation. And so SU V prime and SU prime V, the two triangles, are not only spirally similar, they are spirally congruent. And so it follows U prime V equals UV prime, but U prime V is also the same length as its reflections over line O1, O2. If we reflect U prime over O1, O2, we get U1, and for V, we get V1 prime. So it's also equal to U1, V1 prime. There we go. We have that UV prime equals U1, V1 prime. And so if UV prime equals U1, V1 prime, let's take a moment to go back to the problem statement. We want to prove that it's bisected by line AB. So maybe take a moment to look at this entire set of 4 points and focus on segments U V1 prime and U1 V prime. Now, because these two segments are equal, they have a common midpoint. Let's call that point T. And point T, we conjecture that it lies on AB, and the proof is really simple. Just consider its power with respect to both circles, omega 1 and omega 2. So you'll see that TU1 times TU is equal to TV prime times TV1 prime. But that's obvious because T is the common midpoint of UV1 prime and U1V prime. That means TU1 equals TV prime and TU equals TV1 prime. So yes, T does indeed have the same power with respect to both omega 1 and omega 2, and so it lies on the radical axis of those two circles, which is line AB. So we proved that AB bisects UV1 prime, and the same would hold true if we just reflected V1 prime over a line that is perpendicular to AB to get V. O1, O2 is perpendicular to AB, and if we reflected over O1, O2, it wouldn't change the bisection condition. So UV is also bisected by AB, and we are done. In fact, it's not the only segment that's bisected by AB. Also U prime V prime, because U1 V prime is bisected by AB, and we reflect U1 over O1, O2, which is perpendicular to AB, to get U prime. So U prime V prime, just like U1 V prime, is also bisected by AB. So both UV and U prime V prime are bisected by line AB. So thank you all for watching this YouTube video. The proof is complete. And good luck on the USAMO in less than 10 days. And please follow our channel if you would like to see more videos.